Okay, thanks, Scott. Hello, everyone. I'm Sean Terry, an assistant research scientist at University of Maryland and NASA Goddard. Today, I'll be giving a presentation on behalf of the leaders of this particular study, Mateusz Kapusta and Przemek Mroz from the OGLE collaboration. So some of the microlensers in the room might be familiar with this animation, but I like to show it to motivate high-resolution imaging follow-up and also precursor imaging for microlensing events. So we start with if you can see it, a high-resolution image. This is from Keck, and if we zoom in just on two inconspicuous stars and go into simulation land, these are a source and a lens star, and we know all the stars move on the sky with their relative proper motions many years before a microlensing event. Also, our solar system, of course, moves in the galaxy. At T0, there's a microlensing event, and then the source and the lens star separate from each other on the sky. And so our group and some others have led some high-resolution imaging campaigns several years after microlensing events. And one of the main goals is to directly measure flux coming from the lens object. So if it's a luminous lens, so a host star to a bound planet. Of course, if we're looking for things like FFP lenses or other dark lenses like neutron stars or black holes, then in our late time high-resolution imaging, we would not expect to detect lens flux from the lens object. Another motivation for this type of work is if you can directly measure flux coming from the lens, if it's hosting a planet, for example, you can sort of get much tighter constraints on the physical parameters of the lens system, like the mass of the host star, the mass of the planet, the distance to the lens system, and much more. Okay. So this event in particular, the OGLE 2023 Bulge 524 event, the light curve for it is here on the left. It's a very short duration event. It's a FFP candidate. So you can see the duration on the days on the x-axis is very short. The Einstein time scale is less than half a day, so it's about 10 hours. These are the light curve model parameters on the right. And it is just one FFP candidate among many, but there's some interesting details surrounding this particular event. So it was found to actually be covered by archival Hubble telescope data from 25 years before this event occurred, which is a record time baseline between a high-resolution image of the location of a microlensing event and when the event happened. So the event was covered actually in a HST Cycle 7 program led by Dave here in the room, using the WIFPIC-2 camera, Wide Field Planetary Camera 2 on HST. A few more details about the archival data set. So again, just the program that serendipitously observed it before, many decades before the microlensing event happened, was focused on a completely different set of microlensing objects from the 1990s. And it just so happened that this eventual 2023 event, the source for it that would eventually be lensed, was nearby. So just to put it in perspective, where we're talking typical galactic bulge and galactic center region, the highly extincted dust, the bulge here where typical ground-based microlensing surveys focus, and then just in a pretty typical region in the bulge, I zoom in just in a Aladdin view with the WIFPIC-2, the HST camera outlines, and I'll point out the original subject of this observation is this Macho 96, very old event from 1996. It's this located where that yellow four-pointed star is. And just a few arc minutes away would be the source star that would eventually be microlensed in 2023. approximately here where the blue star is. And one more detail to add, actually, the case of these serendipitous events, there's more than just this one. There's actually quite a few. I'm leading a current program in cycle 32 of HST to confirm some of these serendipitous host detections for lenses, so that the program has about 7 or so events, of which this is the one FFP candidate event in that program. Okay, a quick timeline just of these events. 1997 was the image from Dave's program using WIFPIC-2. Here's just the field and a zoom in on where the source star is in the crosshairs, the background source star, many, 25 years before it would be microlensed by the FFP candidate. There are some nearby unrelated stars that are not related to the microlensing event nearby. 25 years later, the source is microlensed in this light curve. And then 2 years after that, earlier this year, my program revisited the target with a newer instrument on HST called Wide Field Camera 3. So it's a newer camera, it's higher resolution than WIFPIC-2. My observations go a bit deeper, so you can see some fainter stars around the source, as opposed to the lower SNR 1997 data. The quick short story is that there's no obvious host detection in either of these analyses of the old data or the new 2025 data. Okay, in honor of this record-breaking 25-year time baseline, I wanted to make a fun version of this timeline and go take us back to 1997 really quickly. So in 1997, that's me, a very young kid. I found this picture. I took a picture of a picture. Unfortunately, I do have a bowl haircut in 1997. Anyway, enough about me. I looked up some global events from the year 1997. I looked up the highest grossing movie of 1997. Anyone wager a quick guess on what the top movie of 1997 might have been? Jurassic Park? That's a good guess. It's a good. Jurassic Park 2 came out in 1997. Men in Black? No, it's the age-old Titanic, 1997, of course. A little bit harder, more difficult, but I also looked up the top song of 1997. It was Candle in the Wind by Sir Elton John. He actually performed it live at the Princess Diana's funeral in 1997. It's the only time actually Candle in the Wind has been performed live by Elton John. Okay, thanks for indulging my trip back to 1997. We can get back to science. So typically in the high resolution imaging analysis, we do point spread function modeling, fitting to the data. The left just shows a color magnitude diagram of the stars surrounding the target. The source in blue down there is pretty faint with respect to the nearby on the CMD, so it's about 19 or 19 and a half in IMAG. The right are the 1997 images of the source is labeled as star number 3 here, and these 2 nearby neighbor stars. So we perform PSF modeling and fitting and subtracting them and look at the residuals. It's sort of typical process. So the images on the right are the residuals after fitting and subtracting. We do both a 3-star fit. So we fit for the source and then the other 2 blended stars. And then we also do a 4 PSF model fit, where the 4th PSF model would be to fit for a possible host of the FFP candidate, if it's in fact a wide orbiting planet and not a true FFP. The quick short story is the 4 PSF model, the best fit results are improved only by a delta chi squared of 2. So And when you add the fourth PSF model to the fitting, that gives you three additional parameters, the X, Y position, and the flux of the fourth star. So it's essentially no improvement in the four-star fit over three. So we don't have evidence of a host to this FFP candidate, at least in the 1997 data. I will quickly note I did a very similar analysis of the new 2025 data and found essentially the same results. Although in 1997, 25 years before the event, the expected separation between the lens and the source is much larger, obviously, than it is 2025, just 2 years after the event. Okay, I think this is my last slide. So some details on simulations that were done by Mateos and Shemek. So some injection and recovery tests were performed. So this is planting a fake star at different magnitudes and seeing, getting a magnitude limit for a possible host star if there is one. So if it's a bound planet instead of an FFP. The quick results are that 95% of possible hosts brighter than an IMAG of 21.8 should be detectable. And these injection recovery tests are combined with galactic models and also mass luminosity relations, empirical ones, in the I bands and the V bands, which were the pass bands measured by HST, to generate something like this. So the figure on the left is a detection probability as a function of the distance to the lens. So of course, if the lens is closer, if the lens has a host with a planet instead of an FFP, then it would have a higher detection probability the closer it is. Importantly, there's two different measurements here, this n equals 0, n equals 1. So it's quite important to consider the planet hosting probability for bound planets. So this says a host star of a given mass, is equally probable to host a planet of whatever the mass ratio that's measured in the microlensing event. So there's two dependencies here, the no dependence. So the planet mass has no dependence on its host if it has a host that it's orbiting, or the planet mass scales as the host mass to the 1 power. So that's n equals 0 and 1. And the right just shows the probability densities distributions for the possible magnitude of a host if there is a host star. Again, in the two different regimes. So quick results. There's two different interpretations basically for this particular event. So the FFP candidate, its mass basically. So if the FFP candidate is in the foreground disk in front of the bulge, so nearer to us, the mass of the lens is about 9 Earth masses, and if it's a more distant FFP candidate, then its mass is about 58 sub-Saturn-mass FFP. Okay, that's my last slide, and I'm happy to take questions. Thanks.
All right, we have plenty of time for questions. Dave.
So you did have a few stars that were close to the target, both in the 1997 observations, and the more recent one had some fainter targets. What were those separations from the source?
In the 2025 epoch?
Both.
So I mean, the fainter ones, there's no measurement in the 1997 epoch, definitely.
Right, but you have measurement for the 2025.
Yeah, so the expected separation between the host and the lens in 2025 is very small. It's less than a pixel in HST.
No, the question is, what's the separation between the source and the stars you see in the image, right? There's a faint star.
Sure.
The upper left.
Yep.
And
so this, I mean, I would have to go back and look. This is what, 5 pixels times 40 milliarc seconds per pixel on the HST detector. So.
And the separations between the stars you fit in 97?
Well, the faint ones are not detected in 97, but yeah, these two neighbors Actually, I mean, you can kind of see it by eye, actually, in this 8-year difference between the 97 and to 2025. These two neighbors particularly, you can see there's a significant relative motion between them. I don't have the exact numbers to quote. It's by eye, it's 10 pixels times 40 milliarc seconds.
Okay, well, I mean, your
400
limits on a
milliarc
host star depend on what you're assuming about what the separation between the source, between the possible host star and the planet would be.
Correct. Yeah.
So
So
if you allow for sufficiently large separations, then you could have a host star.
Correct. Yeah. So if the planet host separation is 1,000 AU or something super large, and its distance is very close to us, then perhaps, yeah, the separation between one of these neighbors and the source could be consistent with that. Correct. Yeah.
Okay. Okay. Not sure who was next. Maybe David?
Hey, thanks, Sean. David Kipping, Columbia University. So I'm just wondering, this may be a naive question, but about the spectral energy distribution, if you can put constraints on the host star, because even not waiting 3 years, just if the source and the lens are different spectral types, would you not be able to see some differences in the colors?
So while they're still highly blended within an HST PSF, or
indeed, I mean, because we are looking for companions to white dwarfs, for instance, and brown dwarfs using spectral energy distribution. So why not use that same technique here?
So you can. I don't know how much additional information you get so the microlensing model will give you a blending parameter. So it'll say, your source star, which you do clearly measure, which has a significant amount of flux, might be blended with the host, the lens host. So you can basically take the blending or the source flux fraction in different pass bands if you have it measured across different pass bands, and you can say there's excess flux here that's not due to just the source star, so that you can use the excess flux that you measure in X, Y, B, V, I, near IR pass bands and make an SED from it. Yes. You have to make some additional assumptions, like the excess flux that you measure in that blended profile. The excess flux all of it comes from the host and not maybe a companion or an unrelated blended ambient field star. So there's some additional assumptions you'd have to make. Yeah. Best case scenario is directly measuring in multiple epochs a lens as it separates from the source.
Okay, one more quick question. Coming.
Is there any blend flux in the HSC image?
Blend flux and
As in, does the magnitude match the light curve model exactly?
In the 1997 data, yes. I don't. So the publication timeline was, so the 2025 data came in a very advanced stage of the paper, and Shemik's student, we definitely wanted to get him graduated. So I don't know the answer on the 2025 data, but in the 1997 data, the answer is
But there was also a 24 data, right? Wait,
no 2024
okay.
data.
Sorry,
Yeah, just these two epochs, 97
thanks.
2025. Yeah.
Okay, we should move on. Thanks. Let's thank Sean again.